In this video, I will show you an AC circuit example. I will show you a series RLC circuit. See, I have a resistor of 15 ohm, an inductor with inductance 20 millihenry, a capacitor with capacitance 100 microfarad. This R, L and C are connected in series, and in this RLC series circuit we are applying an alternating voltage V. Here V is equal to 169.7 sine 377 t plus 0 degree. In this RLC circuit, we have to calculate the total impedance, total current, phase angle, voltage across each element, power factor, apparent power, real or average power and reactive power. Finally, we have to draw the phasor diagram and power triangle of the circuit. As we are applying a sinusoidal voltage in the circuit, let me compare the applied voltage with a standard sinusoidal equation. V equal to Vm sine omega t plus initial phase angle of the applied voltage phi V. Here you will see maximum value of voltage, that means Vm is equal to 169.7 volt. The phase angle of the voltage phi V is equal to 0 degree. As we know the maximum value of the applied voltage and the phase angle, we can calculate the RMS value of voltage. Vrms will be equal to Vm phase angle phi V over root 2. 169.7 phase angle 0 degree over root over 2 volt. This will be equal to 120 with phase angle 0 degree or 120 plus J0 volt. From this equation, we can write down the angular frequency of the applied voltage omega, which is equal to 377, and we know that omega is equal to twice phi f, from which I can write down the frequency of the applied voltage is equal to 60 Hz. This is a series RLC circuit. There could be three possible cases. In this circuit, the first case could be inductive reactance XL could be greater than capacitive reactance XC. In that case, the circuit will be an inductive circuit. XL could be less than XC. In that case, the circuit will be a capacitive circuit. Third case could be inductive reactance XL could be equal to capacitive reactance XC. This is known as resonance condition of the RLC series circuit. In that case, the circuit will be a purely resistive circuit. At first, we have to calculate the impedance of this RLC series circuit. we know that the total impedance of a RLC series circuit is given by R plus J XL minus XC. Let's say this is equation number 1. How do we calculate the inductive reactance XL? XL is equal to twice phi F L. Here F is 60. Inductive reactance is equal to 20 millihenry or 20 into 10 to the power minus 3. This will be equal to 7.54 ohm. The capacitive reactance XC could be 1 over twice pi FC. 1 over twice pi 60 into capacitance is 100 microfarad, that means 100 into 10 to the power minus 6. So it will be equal to 26.54 ohm. So we know the value of impedance because Z equal to R. The value of R is 15 plus J, here XL is 7.54. XC is equal to 26.54. So the total impedance will be equal to 15 minus J 19. This is known as rectangular form. In polar form, our impedance Z will be equal to 24.21. Phase angle will be minus 51.71 degree ohm. So this is the value of total impedance in rectangular or in polar form. After that, we have to calculate the total current in the circuit. As we are applying an alternating voltage in the circuit, we will get an alternating current. Let's say that current is I. The total current in the circuit I will be the ratio of total voltage over total impedance. Here total voltage is equal to RMS value of voltage 120 degree, phase angle 0 degree, and the total value of impedance is 24.21. Phase angle will be minus 51.71 degree. So here the total current I is equal to 4.96 with phase angle 51.71 degree. Now see, this 4.96 will indicate the value of RMS current. IRMS is equal to 4.96 ampere. This 51.71 degree is known as the phase angle of the current phi I. This will be equal to 51.71 degree. After calculating total current, we have to calculate the phase angle. Phase angle, that means we have to calculate the phase difference between the total voltage and total current in the circuit. Phase angle or phase difference is the phase angle difference between the current and voltage. In the circuit, the applied voltage has value of 120, phase angle 0 degree. That means phi V is equal to 0 degree, and here the current I is equal to 4.96 with phase angle 51.71 degree. That means phi I is equal to 51.71 degree. Now see, in the circuit, the value of inductive reactance XL is equal to 7.54 ohm. Capacitive reactance XC is equal to 26.54 ohm. As inductive reactance XL is less than capacitive reactance. So this is a capacitive circuit. In a capacitive circuit, current I leads voltage V by an angle equal to phi D. So here phase angle or phase difference phi D will be equal to phi I minus phi V. So I will get 51.71 degree minus 0 degree, which will be equal to 51.71 degree. That means in the circuit, the current I leads the applied voltage V by an angle of 51.71 degree. What does that mean? If I want to draw sinusoidal voltage and sinusoidal current in the same scale, see, V will start from 0 degree. Let's say in the y-axis I am taking V and I will get a sinusoidal voltage like this. Our current I will start from, let's say, 51.71 degree ahead from the origin of the voltage. Let's say that will start from here. Therefore you will see the current I will be 51.71 degree ahead of the voltage, or I leads V by an angle of 51.71 degree. After that, I will calculate the power factor of the circuit. I will show you the voltage across each element, that means voltage across resistor, inductor and capacitor, when I will be drawing the phasor diagram of the circuit. Now I will show you the power factor. In the circuit, the phase difference between the voltage and current is equal to 51.71 degree. So power factor is the cosine of the phase difference or phase angle. So here cosine 51.71 degree will be equal to 0.62, or we can calculate the power factor by taking the ratio of magnitude of resistance and magnitude of impedance. Here resistance is 15 and impedance is equal to 24.21, or this will be equal to 0.62. This is the power factor. After that I will calculate apparent power, real or average power and reactive power. In the circuit, RMS value of voltage is 120 volt. RMS value of current IRMS is equal to 4.96 ampere, and the phase difference between the voltage and current phi d is equal to 51.71 degree. In the circuit, apparent power. Apparent power S is the multiplication of RMS value of voltage and RMS value of current, VIRMS and IRMS. Here VRMS is equal to 120 volt, IRMS is equal to 4.96 ampere. So we will get 595.2 volt ampere. After that, I will calculate real power or true power or active power or average power. Which is equal to VRMS IRMS cosine phi d. We can calculate this power by multiplying IRMS square with resistance. These two should give very close value. Here VRMS is equal to 120, IRMS is equal to 4.96 ampere, and cosine of phi d. So here we will get 368.8 watt. After that, I will calculate reactive power. Reactive power is expressed with Q. Real power is expressed with P. Q is equal to VRMS IRMS sine phi d. (120) into 4.96 into sine of 51.71 degree. This will be equal to 467.16 var. After calculating the power components, I will draw the power triangle. Power triangle is the right angle representation of the real power, reactive power and the apparent power in a right triangle. So in the circuit, we get the real power. We represent the real power in the direction of plus x. We represent the reactive power either in the direction of plus y or minus y axis. If the reactive power is because of the capacitance, it will go in minus y axis. If the reactive power is due to the inductive component, it will be in the plus y axis, and the apparent power will indicate the Pythagorean of real and reactive power. So here at first I will start with the real power. I will indicate the real power with, let's say, OA, reactive power with AB, and apparent power with OB. Here the real power is 368.8 watt. We will take real power in plus x direction. This OA will indicate the real power. whose magnitude is equal to 368.8 watt. This is the real power axis. Now see, in this circuit, XL is less than XC, for which we say that this is a capacitive circuit. So the reactive power or the net reactive power will be due to the capacitance. Therefore the reactive power will go in the direction of minus y, and it will start from the A. Let's say this AB represents that reactive power 467.16 var. See, this angle will be 90 degree. Now see, if I join this O and B, this OB will indicate the apparent power, which is equal to 595.2 volt ampere, as we represents the real power, reactive power and the apparent power in a right triangle. This OAB will be the power triangle. Where the hypotenuse OB will be the square root of the sum of real power 368.8 whole square plus reactive power 467.16 whole square, and this will be around 595.2 VA. Okay, so this is the real power, this is reactive power, and OB indicates the apparent power. Now I will show you how to draw the phasor diagram by using the voltage across each element. So I will solve this question number 4 and part of question number 6. While drawing the phasor diagram or vector diagram of a circuit, we take that component as reference which remains same all over the circuit. As this is a series RLC circuit, in a series circuit, current I remains same all over the circuit. So here I will take the current I as our reference phasor. Here current is 4.96 ampere. I will indicate the current phasor with vector OA. I will take this in plus X direction. So let's say this OA is our reference phasor I. After that we will calculate the voltage across each element. Voltage across the resistor VR will be the multiplication of phasor current I and the value of resistance. Here current is 4.96 and resistance is 15 ohm. So we will get 74.4 volt. If we look at the phasor relationship between the voltage and current across a resistor, if we take the current in this direction, the voltage across the resistor will go in the same direction, or in a resistor V and I are in phase. So we will take VR in the direction of phasor current. Let's say this OB will indicate our VR. After that we will calculate the voltage across the inductance IXL. Here I is equal to 4.96 and inductive reactance is equal to 7.54, which will be equal to 37.4 volt. We will indicate the inductive reactance VL with OC phasor. See, if we look at the voltage and current relationship in an inductor, the voltage across the inductor always leads the current by an angle of 90 degree. So we are taking the current phasor in this direction. The voltage will go in this direction VL, which I will indicate with OC. The VL will lead the current by an angle of 90 degree. VL is equal to 37.4 volt. Now we will calculate voltage across the capacitor. VC will be equal to IXC. I is equal to 4.96. XC is equal to 7.26.54, which will be equal to 131.64 volt. I will indicate this phasor with OD. If we look at the current and phasor relationship in a capacitor, we will see the voltage across the capacitor VC lags the current by an angle of 90 degree. So if I take the current phasor in this direction, VC phasor lags the voltage by an angle of 90 degree. VC, we will take VC in this direction and VC will be OD phasor. Now see, at this point VL and VC are acting in opposite direction. As we have two vectors are acting in the opposite direction, we can say that VL and VC will try to cancel each other. Therefore the resultant will be the difference of VL and VC. Here VC is greater than VL, so I can say that the resultant will be equal to VC minus VL. Here VC minus VL vector will be equal to 94.24 volt. Let's say I will indicate that VC minus VL phasor with OE. VL is equal to 37.4 volt. VC is equal to 131.64 volt, and the difference will be in this direction. Let's say this is that OE phasor, which will indicate the difference VC minus VL, which is equal to 94.24 volt. Now see, as we have OE vector, we can draw an equal vector at the point B, which will be the same as this OE. So this BF is the equal vector of OE, which will indicate VC minus VL. Now see, we have VR here and VC minus VL here. If I add this O and F, this will indicate the total voltage V in the circuit. This angle will be 90 degree. Therefore this will be the hypotenuse of this right triangle. Therefore this phasor diagram is also known as voltage triangle. Now see, what will be the magnitude of this V? V will be the Pythagorean of VR and VC minus VL. That means V will be equal to VR square plus VC minus VL whole square. You will see it will be approximately 120 volt. So VR is equal to 74.4 volt. VC minus VL is equal to 94.24 volt, and their resultant will be equal to 120 volt. Now see, from this voltage triangle you will see, as this is the total voltage V, this I is the total current in the circuit. The phase difference between voltage and current will be exactly equal to 51.71 degree. From this phasor diagram or voltage triangle, we can also say that here current I leads V by an angle of 51.71 degree. Okay, that's it. Thank you.